Start the recording. And we can go from a half hour from now. Let's plan on going to 4:15 if that works for you.
Works fine for me.
Okay. All right. I want to make sure you get comfortable with this concept here, because a huge part of geometry is going to be comparing similar triangles. Remember, similar only means they have the same three angles. Okay? So, if I have a triangle over here that is a right triangle, and that side's 30, and this side's 10, what's this side here, and what's this side here going to be? Remember, the first thing you need to do is come up with the similarity ratio.
So,
what's the similarity ratio between this large triangle and the appropriate one over here?
Oh, okay.
How much bigger is this triangle than this one?
Divide by 5.
It's 5 times bigger, right? In other words, and I don't mean area. When I say how much bigger, I mean how much bigger is the same hypotenuse. In other words, these two triangles are similar, the two that I've circled, because this has to be 60 up there. So this is a 30, 60, 90, and this is a 30, 60, 90. So once you figure out what the similarity ratio is, every side of this triangle is going to be that similarity ratio times these sides. So if the similarity ratio is 5, what's the vertical side?
5.
What's the horizontal side?
5 times the square root of 3.
Right. Okay. Now I'm going to change it, make it a little bit harder. Hold on, let me close my door. 1 minute. Okay. Now what is the similarity ratio?
Square root of 3.
Not quite. It's the square root of 6 divided by 2, which is not the square root of 3. If it was the square root of 6 divided by the square root of 2, that would be the square root of 3. But this is just square root of 6 divided by 2.
Okay.
That's the similarity ratio. What's this horizontal side here?
I don't know.
Well, take the similarity ratio and multiply it by the smaller triangle's similar side. In other words, our similarity ratio is the ratio of the two hypotenuses. It's got to be the same ratio for this side that's opposite the 60-degree angle. So I'm going to multiply that by square root of 3. What's square root of 6 divided by 2 times square root of 3?
Square root of 18 divided by 2.
Yeah. Now, can you reduce square root of 18?
Square root of 9 times square root of 2.
Okay, which is 3 square roots of 2 divided still by the 2. That's what that side is right there. Okay. So it's all about finding the similarity ratio and then multiplying the similarity ratio times the appropriate side of the unit triangle. What's this vertical side right there?
Square root of 6 divided by 2.
Okay, let's do one more. This time I'm going to make it a 45, 45, 90. And I'm going to make this side 3. What are the vertical and the horizontal sides?
Square root of 2 divided by 3.
When you do a similarity ratio, you can do it either way. You can do it small to big. I find that it's much better if you do it big to small. 3 is bigger than square root of 2. So let's make our similarity ratio that. In other words, that's how much bigger the triangle, each side of the triangle on the right is versus the triangle on the left.
All right.
What does that simplify to? Or I should say, what does that rationalize to?
I'm not sure.
How do we rationalize that? It has an irrational denominator, which is not a, can't have that.
So square it?
Not square it. In other words, if I square top and bottom, I change the number. Notice that if I take 3 halves and I square it, it becomes 9/4. That's not the same number as 3 halves. So the one thing you cannot do with fractions is square top and bottom. The only thing you can do is multiply them by the number 1. Well, in this case, my number 1 is square root of 2 divided by square root of 2. That makes the numerator that, and the denominator that. So this is actually my similarity ratio. It's the same number as this, it's just expressed better. Okay? So what is this vertical side over here going to be?
3 times the square root of 2 over 2.
And the horizontal side?
3 times the square root of 2 over 2.
Okay. Now that's the problem. I don't give you the hypotenuse. What's the hypotenuse? What's the vertical side?
Vertical side is 3.
What's the hypotenuse?
3 times the square root of 2.
Okay. That's really as hard as they get. As long as you're dealing with these two special triangles. Now, as long as we're talking about similar triangles, let's talk about, okay, that's not a right triangle. I don't even know what the angles are, but I'm going to say that it's similar to this triangle. Well, if I give you only one side of this triangle over here, and I say that these two things are aligned properly, what is this side going to be?
14.
Yeah, the similarity ratio is 2 to 1. So I'm going to take that 2 to 1 and multiply it by 7. And what's this side down here?
16.
Yeah. And those two triangles are similar. Now what you're going to learn in geometry is that there's two words. There's congruent and there is similar. Similar merely means it's exactly the same shape, meaning it has the same 3 angles. Congruent means equal. In other words, if I say these two triangles are congruent, they not only have the same 3 angles, but they have the same 3 sides. It's got to be a 6, 7, 8. Only that would be congruent. Remember, congruent is just another word for equal. All right. Remember these dimensions. What's opposite the 30 on this one?
1.
What's opposite the 60?
1.
That's on this one over here. This is the isosceles one. This is not an isosceles triangle. In other words, the side opposite the 60 cannot be the same as the side opposite the 30. One thing in geometry is if you have a big angle, the side opposite it has to be bigger than the side opposite a smaller angle. In other words, by definition, I know this side down here has to be bigger than 1, merely because the 60-degree angle is bigger than the 30. This side is square root of 3.
All right.
Now, if you had to, you could use the Pythagorean Theorem. What's this hypotenuse equal to? Use the Pythagorean Theorem. We've practiced that, haven't we?
Yes.
Okay. So square root of the square of the other two sides.
Okay, so 2.
Right. This one over here is also, I call it a unit triangle, meaning the side opposite the smallest angle has to be 1. Well, if that side's 1, this side's 1, because those two angles are equal, their opposite sides have to be equal. And in using the Pythagorean Theorem, what's the hypotenuse?
1. Or square root of 2.
Square root of 2. Now, I could just as easily, for purposes of similar triangles, I could just as easily call this this. It's only the ratios that we care about. This triangle over here is similar to this triangle here. And if I had, say, a 45-45 triangle that had a side of 20, I could compare it to either one of them. If I compare it to this one over here, what's the similarity ratio?
Times 2.
Yeah, which means the hypotenuse would be 20 root 2, right?
Mm-hmm.
Well, if I compare it to my unit one, what's the similarity ratio?
Times 20. 20 to 1.
So I still get the right hypotenuse.
Mm-hmm.
In other words, I don't have to compare it to anything in particular. I just have to pick a triangle that I can compare it to that I know the dimensions of. So these are the two that I use. All right, let's go on. I think you got that down pretty good. I'm not sure. Does this look familiar? Have we done this? I think maybe we've done it.
This doesn't look familiar.
Okay, let's do it then. So we want to figure out the area of that trapezoid.
Okay.
And it is an isosceles trapezoid. First of all, the definition of a trapezoid is it is a quadrilateral. It's 4 sides. And 2 of the sides are parallel and opposite, and 2 are not. You can see that side BC is parallel to AD, and AB is not parallel to CD. Okay? So, we can do a couple of things. Let's break that trapezoid up into a rectangle and 2 triangles. Like this. In other words, I'm going to use the line they have, and then I'm going to drop a line there. Because that side's 5 and that side's 5, I know these 2 triangles are similar. Okay? This side's 8. And this side's 3. and this is a right angle. What does this side here have to be? Use the Pythagorean Theorem again.
3.
What is it?
Is it 3?
No.
So
Remember, it's the square root of the hypotenuse squared minus the other short side squared. So it's the square root of 25 minus 9. What is that?
16.
Square root of 16 is 4.
Mm-hmm.
That is another extremely important right triangle that you will be constantly presented with. Is one whose short sides are 3 and 4 and whose hypotenuse is 5. It's famous because it is the smallest perfect Pythagorean triangle. In other words, there is no 2, 3, 4 or 1, 2, 3. There's 3, 4, 5 and that's it. The next smallest one is 5, 12, 13. Okay? So, if that is a 3, 4, 5, and we know that this is similar, that's also got to be a 3, 4, 5. What's this dimension here?
8.
What's the area of the rectangle?
4.
What's the area of this triangle here?
6.
And the other one?
6.
Add them all up, you get 36. That's the answer. Number 8. What is the area of a circle with a diameter of 8 inches? Always start these out with the general formula. What's the general formula for the area of a circle?
Pi r squared.
If its diameter is 8, what's its radius?
Sorry, what?
It tells us that the diameter is 8. We need to know its radius. What is its radius?
4.
So the area is pi 4 squared, 16 pi. And the other thing that happens at geometry is you stop converting pi. You give most of the time. You'll do it both ways for a while. But most of the time you're going to give your answer as 16 pi. You're not going to convert that thing to 3.14 and come up with an approximation.
Yeah.
55. Let's go to the next page. Now, a lot of these things, there's just no way you're going to know how to do it because you haven't had geometry yet. But the things that it tests here are worth knowing. When you get into geometry, you're gonna be better off having known this stuff. Trying to think of how to explain this one. When you have a circle, the distance from one point on the circumference all the way around can be measured as a circumference or it can be measured as an arc. That's 360 degrees. Likewise, if I have a segment of the circle, a pi, cut out, and this is 40-degree angle here, that is a 40-degree arc length. Not 360 degree, but 40 degree. Now, if the radius of this circle is 9, what is the circumference of this circle? The entire circumference.
18.
Well, what's the general formula for circumference?
Oh, I don't know the.
It's got the same three numbers as the area, only it's 2 pi r instead of pi r squared. In other words, one way to think of the circumference is start with the area and just bring the 2 down in front. And that's the circumference. Okay? So if my radius is 9, what's the length around the circumference? R is 9.
What I'm thinking of doesn't even match any of the answers.
Oh, well, no, we're not there yet. I'm just taking you through it step by step. The total circumference is going to be 18 pi, right?
Yeah.
Okay. Well, this represents a part of the circumference. What part? How much? All the way around is 360 degrees. So what part is 40 degrees?
1/9.
1/9, exactly. So the measurement of this piece of the arc from here to here, if that was a piece of string and you could straighten it out and you wanted to know how long it was, that's 1/9 of the circumference. Or in this case, 2 pi.
All right.
Okay? So when you're talking circles like this, you actually have a couple of different ways of measuring this thing from A to B. One is the length of it. That's what we just did. It's 2 pi long, about, 6.2 units. But the other way to measure this is arc length. That's also 40 degrees. If I measure it as an arc length, or rather an arc in degrees, then that's the other way to measure it.
Okay.
When you see a shaded region problem, what kind of problem is it?
I don't know.
Maybe I've never told you. I probably haven't. Shaded region problems in geometry are almost always subtraction problems.
Okay.
Okay? In other words, I don't know any geometry that allows me to calculate this area. We don't have any formula for that shape. What I do know is how to calculate the area of the square. And I know how to calculate the area of half of the circle. If AD is 10, what's the area of the square?
100.
What's the area of the entire circle?
Entire circle.
What's its radius?
AO.
Right. Well, how does that compare to AD? AD is 10 units long. How long is AO?
5 units.
Yeah, because the radius is always half the diameter, and AB is also the diameter of that circle. So I know that AO is 5. So what's the area of the entire circle?
25 pi.
What's the area of half of that?
Area of half.
No, and I don't want a number. I want you to just divide it by 2, like that. In other words, this is the area of this semicircle.
All right.
So if I take the area of the square and subtract out 25 pi over 2, that's going to give me the area of the shaded region. Answer H.
All right.
But just remember in geometry, when you see shaded region problems, they are subtraction problems. All right. Okay, I'm not sure how we started out on triangles. We should have actually started on lines and angles, which is this section here. These are pretty basic. What are the sum of these three angles?
180 degrees.
So what's x?
50.
Good. Now, you understand how they designate angles, right? When they say angle AOE, you start at A, go to O, go to E, they're talking about this angle right here.
Yeah.
Okay.
Be 145 degrees, wouldn't it?
Yeah, and you figure out that this one was 35, and it was the supplement to that. Is that what you did? How'd you get that answer? You merely took it as the vertical angle to these two. That's a faster way to do it. In other words, if you have this, angle 1 is always equal to that angle 1. And angle 2 is always equal to that angle 2 from vertical angles. Well, we actually had something similar to that here. The angle that's made up from BOD is 145 degrees, right?
Mm-hmm.
And that's vertical to AOE. In other words, if I eliminate that line right there, all I have is two intersecting lines, and that angle equals that angle. So actually the way you did it is faster than the way I was going to show you to do it. We haven't done these, have we?
No, we haven't.
Okay. I don't know how I have them out of order on my thing, but I do. In the figure above, excuse me, wrong figure for you. What is the? Let me draw this. Or let me point. You can see where I'm pointing, right?
Yeah.
What's this angle right here?
30 degrees.
What's the sum of the four lettered angles?
360.
Well, it's 360 if I count to two, this 30 degree and this 30 degree. But notice that each of these don't include that. So what would the sum of x, w, y, and z be? It would be 360 around the entire thing.
330.
This one's also 30. You have to subtract both of the 30 degree angles from 360.
So 300.
300, exactly.
Okay.
What's the value of x and y here? X plus y.
90.
Good. I wondered why we were starting in such advanced geometry. I meant to start you here. I just wasn't paying enough attention. So if y equals 5 times, if the measurement of y equals 5 times the measurement of x, then what's x equal to?
45 degrees. 45.
How'd you do it?
I just kind of had to rationalize it a little bit.
Well, let's set up an algebraic equation. What can I say about x plus y? What's that equal to? In other words, whenever you have a straight line intersecting with another line, these two angles are always supplementary.
Okay, so 180.
Okay. And what is y equal to? 5x, right? So in place of y, I'm going to put 5x. Now I'm going to solve this equation. What is x plus 5x?
6x.
Now what is x?
30.
That's it. You will find that geometry is at least half algebra. It's all about setting up equations and solving them.
All right.
Okay, this is very similar to the other one we did on the previous page. That's a 90-degree angle. What's x?
45.
What do these three have to total?
No. 180.
Since this is a 91, that means these two have to total 90.
Oh, so 50?
Right. That's called complementary. If two angles are complementary, they have to total 90.
All right.
If they're supplementary, they have to total 180. Those are definitely two good terms to remember. In a right triangle, no matter what its dimensions, if I have a right triangle, angles 1 and 2 are always complementary. Okay, I just looked at my time. I realize we've gone over a little bit, which I don't have any problem with, but you probably don't want to. So,
No.
But we'll pick up from here next time, next Monday. I will just, next Monday, text you the meeting ID number again like I did today.
All right.
Want me to give you any warning, or are you going to be ready for it at 3:30?
I'll be ready for it.
Sounds good. Cole, have a good week. I'll talk to you next Monday.
All right. Talk to you next month.
Bye-bye.
Bye-bye.